Thank you. I'm going to talk about cyclic tipping in cyclic systems and going to introduce what we call phase sensitive tipping. But first, I would like to mention that this talk is a collaborative work with Rebecca Tyson from the University of British Columbia and my mentor here at University College Cork, Sebastian Vidwarek. Um, yeah, so as an example of a cyclic system, I'm going to look into the Rosenzweig-MacArthur predator-prey model, which is, as you can see here, it's two nonlinear ODEs that represent the change in time with the density of prey and predator. So the density of prey is going to be given by N, the density of predator is going to be given by P. In the prey equation, you can see that it consists of logistic growth and a functional response, which represents the interaction between prey and the predator. We also added this term here to give rise to an Ali effect. So whenever you have a low density of prey, that would mean that it's going to go extinct. On the predator equation, it consists of the functional response itself and the mortality rate of predator. We assume that the carrying capacity of the system is giving, it varies with time and it varies in a piecewise constant sense. So that's why I'm denoting I'm making this parameter R time dependent and fixing the other parameters and mark them in green. If you just forget about the time dependency of R for a moment and look at the bifurcation diagram in figure B in this slide, you can see with respect to R, we have at most 4 different equilibrium in the system. One of them, which is E3 in here, is a coexistence equilibrium in the sense that it gives you a non-zero density of prey and non-zero density of predator. This equilibrium go through Hopf bifurcation, where it gives rise to a stable limit cycle, and that limit cycle again vanishes at homoclinic bifurcation. But between the homoclinic and the Hopf bifurcation, the system is going to be bistable. One stable state is the extinction state on the origin, where you have 0 density of prey, 0 density of predator, and the other stable state is the oscillatory coexistence. So you would think that if you limit your climate variability in between these two bifurcations, bifurcation points, then the system is going to keep isolating, oscillating without any transition. But here in this example, where I give you this time series of R of t, that we keep R of t piecewise constant over a certain time interval, and the length of these time intervals is basically random variable, and the values of R at each of these time intervals is random variable itself as well. So you look at the response of the system over here in subfigure C, and you see the system oscillate a little bit, and then at some point it go to extinction. And obviously, if you look at the bifurcation diagram, you can't explain this behavior from the bifurcation diagram. To give you an intuitive understanding of this kind of transition, I have this animated example where I plot the phase space of the system over here with the limit cycle that varies with R, and the state of the system that's given by this black dot, the time series of R of t over here, and the time profile of the densities of prey and predator over here. So if I run this animation, you can see that as R changing, the limit cycle is changing as well. And the state of the system that is represented by this black dot try to keep track of the changing limit cycle, and that keeps happening until you get this case. And you can see that you still have the limit cycle is still around and it's still stable. However, you have the state of the system stop tracking the limit cycle and goes to the extinction state. Um, as we learned from Orica's Feudal talk yesterday, that sometimes to understand these kind of transitions, you have to look into the basin of traction of the states that you are considering, in addition to the bifurcation of the state. So here I'm plotting the threshold between or the boundary of the basin of traction of the limit cycle, and it is going to be a threshold between two a basin of attractions, the basin of attraction for the limit cycle and the basin of attraction for the extinction state. And if I run the movie again, you can see that is not just the limit cycle is changing with time, but the boundary of the basin of attraction is changing as well. And as we approach the tipping point in this experiment, I'll freeze the movie to have a look what's going on. So here we go. And you see that the state of the system at the tipping point is actually outside the basin of attraction of the limit cycle. And now it's natural to think that the state of the system is going to go to the extinction state instead of keep tracking the limit cycle. And it doesn't matter how you change your parameter afterward, because the state of the system is already in a steady state. So to give further mathematical understanding of this behavior, we put together some mathematical theory based on Basin instability theory that has been introduced by Sebastian Bidwick and Paul O'Keefe in a recently published paper in the SIAM journal. And they discussed Basin instability for equilibria. And now we are extending this theory to include limit cycles. So Bayesian instability is a property of the autonomous system. So we are assuming that R is not time dependent, and we consider a continuous parameter path delta R with a family of hyperbolic attracting limit cycles. And we assume that this family varies C smoothly with R. In a sense, there is no bifurcation. And now we consider the closure of the basin of traction of this limit cycles. We say that this limit cycle is basin unstable on the path delta R if there are 2 points on the path that these are R1 and R2, such that the limit cycle at R1 is not fully included in the basin of traction of gamma R2.
2 minutes left, Hassan.
That's fine. To help you understand this mathematical jargon here, I have this picture here where I plot the limit cycle gamma of R1 and compare it with the threshold of the boundary of the basin of traction for R2. And you can see there is this red part of the limit cycle lies outside the basin of traction of R2. And in a sense that if you have a climate variability that changes your R from R1 to R2, and you happen to be on this part of the limit cycle, then you will be having this tipping. And since this tipping would happen from certain phases of the cycle, we call it phase sensitive tipping. Just to conclude, we identify the phase of the cycle as a new critical factor for tipping points in cyclic systems, in addition to the well-known factors such as bifurcation rate and noise. We also would like to point out that this effect of phase-sensitive tipping is is pretty robust in predator-prey systems. So for the Rosenzweig-MacArthur, for example, we identify an entire region in the parameter space where this phase-sensitive tipping can happen. And also we have been looking at another example of predator-prey system, which is the main model, and it's introduced by Robert May in the 70s, and we have been able to identify similar behavior. And finally, one might think that non-stationary systems, sorry, are likely to have this phase-sensitive tipping. And as example here, we can look at the investment in economies of developing countries. As someone from who lived in Iraq during the war of 2003 and afterward, I've been witness on the massive amount of investment in the Iraqi economy, and everybody was saying that we have great potential and everything is going to be all right. And yet, 17 years from there, we still the economy is crumbling, and none of these promises has been fulfilled basically. And to be clear, that I'm not saying that probably we have a better way of doing it. Probably there is not, but what I'm saying is that if there is a possibility to a good transition from a bad state of the economy to a good state of the economy, then what you might be want to do is to look at the Basin instability of the phases of the economy, and then identify the phases that might give you the desired transition, and then you inject all of the investment in the system during these phases and hope for the best. I don't want to speculate any further, so I'll leave it here, and I would like to thank you again for your attention.